All right, guys, we got a couple moments before we're going to really get this party started. So if you have any questions, comments, concerns, go ahead and let me know, and we can go ahead and talk about anything you guys want to talk about. And then we will obviously start getting into the actual class stuff. Zach, where are you at right now?
I'm at my internship.
Why aren't you wearing a mask?
I'm kind of like, I don't know. I guess I should be. I wasn't really around anyone besides our nutritionist.
Who's literally right
Put it
behind
on.
you. Do you not care about her?
Yeah,
Do you not care about her health?
I do. Now you made me feel bad. It's on now.
That's okay. I come from my family is very much so a lot of Irish Catholics, so we're really big on guilt.
I'm not Catholic, but a lot of my family is also Irish.
No, it's all good. And Catherine, as far as the homework quiz, there's one question that needed graded. That's going to happen on occasion where Blackboard is, well, Blackboard, and if for some reason it didn't take all of my coding for how I wrote in all the questions. So that just means I just have to go manually and grade that question. So if you think you got the question wrong, take the quiz again. Remember, it's always going to take your highest grade. And I'll resolve that one question on that one quiz, because it'll probably come up a couple times with different chapters throughout the semester. So don't let it drive you up the wall. So
yeah, it's fine. I went ahead and took it again.
Smart. So I think, well, it's 125, so we're starting up either way. And we left off talking about how skeletal muscle contracts. So the first thing we're going to do is we have an action potential that's generated from our brain. Goes down the motor neuron all the way until it gets to that neuromuscular junction, okay? Now, that axon is going to release a vesicle. Vesicle is just essentially a packet of what's known as acetylcholine. Acetylcholine is that neurotransmitter that's going to go across the neuromuscular junction and then eventually bind to what's known as the ligand-gated receptor. When it binds to that receptor, next to that receptor is a channel, and that channel opens and allows sodium to go into the muscle cell. When the sodium goes into the cell, it's going to cause the resting polarity to go up. As the polarity keeps going upwards, eventually it's going to hit what's known as threshold. When it hits the threshold, that's when you're going to have the voltage-gated channels open, and when those open, now sodium rushes in really quickly, and we have an action potential. Now that action potential now is going to go ahead and travel out of the neuromuscular junction, down the plasma lemma, and into the T-tubules. So what you guys are seeing right over here. When it goes into those T-tubules, it's going to go through what's known as the DHP and ryanodine receptors immediately into the sarcoplastic reticulum in skeletal muscle. Once that action potential is in the sarcoplastic reticulum, calcium is going to be released from the protein known as calsequestrin. And this calcium is now going to go into the sarcoplasm. Once it gets into the sarcoplasm, it's going to bind to what's known as troponin. Now, when calcium binds to troponin, specifically troponin C, it's going to cause troponin to move tropomyosin off of actin. Tropomyosin is what's literally keeping actin or keeping myosin from grabbing hold of actin, because it's blocking those binding sites when the muscle is at rest. And this is going to happen effectively as long as there happens to be that calcium available. So now actin is going to be grabbed by myosin. Myosin is going to ratchet it forward, grab it again, ratchet it forward, grab it in, ratchet it forward, pulling it into the midline until calcium is going to be pumped back into the sarcoplastic reticulum, because there's no longer an action potential, and it's going to be rebound to calsequestrin. It's a lot. The easiest way to go through it is to just keep going through it, okay? I don't have any cute mnemonic devices or anything else that's really going to help you guys go through this super fast, other than it's going to be repetition as we practice. So you've got to go and read through it. You have to think your way through it, and you have to take some time and sit down with it. Now, that was a lot. This is recorded, so you guys can re-listen to this as many times as you want. Is there anything you guys want me to go ahead and just touch on right now? You can throw it up in the chat, or you can throw it up in the, or just unmute yourself, your choice.
Can you go back over the calcium binding to troponin?
No worries. So calcium at rest in the sarcoplasm is going to be bound to calsequestrin. When the action potential goes in there, calcium is going to be, the voltage change literally changes the configuration of the protein, so calcium effectively pops out of it. Calcium then is going to go into the sarcoplasm. Once it's in there, it's going to bind to what is known as troponin. When it binds to troponin, troponin is now going to ratchet, effectively moving tropomyosin off of actin. So it's no longer blocking the binding sites on actin where myosin grabs hold and pulls it in through the center. Is it good? All right. So when we're talking about that myosin grabbing hold of actin, guys, remember the myosin is going to be pulling those actin strands into the center line. That's contraction. When they're going further apart, that's relaxation, or an eccentric contraction where the muscle is now lengthening. Okay. Now, when it comes to the actual power stroke, so this is myosin grabbing, pulling forward, releasing, springing back, grabbing, pulling forward. ATP is actually important for getting myosin to let go of actin. So what's going to happen is, as soon as myosin can, it's going to grab and ratchet forward. ATP is going to go ahead and bind into the ATP site for the myosin head, which is going to cause myosin to release. That ATP is going to be hydrolyzed into ADP and a phosphate, which is going to cause it to cock back. And then it's going to grab again and pull itself forward, grab again, pull itself forward, and keep doing that ratchet effect. So make sure you also sit down and understand this. Now, the question that I will pose to you guys, because we just talked about how sodium is important in muscle contraction and calcium is important in muscle contraction, and specifically calcium is important in muscle relaxation. So if we can't get that calcium out of the sarcoplasmic reticulum, we're going to still have our muscle cramping. So hence one of the potential mechanisms for muscular cramping. Now, when it comes to looking at myosin crossbridging in ATP, so this could be an issue with energetic insufficiency. Once, and I know I've said it before, but I want you guys to either throw it up in the chat or unmute yourself. If we don't have ATP or enough ATP inside of our sarcoplasm, what is it that muscle is unable to do? Is it contract or relax? Yes, John, good job. It's unable to relax. So I'm sure all of you guys have done a real hard workout or something along those lines, and you literally like, I just want to relax, but my muscle keeps cramping up on me. I'm not dehydrated. I've had enough electrolytes. It's not an issue that way. Instead, it's an issue of literally you don't have the energy in your cell to get it to relax. How many of you, do any of you guys know what rigor mortis is? Rigor mortis. And you can unmute or you can throw it up in the chat. Okay, what is it, Catherine?
It's like what happens whenever you die and all of your like muscles just stick up and stuff. I don't really know how to explain it.
Yeah, no worries. So unfortunately, after you pass away, after a certain period of time, your muscles will literally just contract. They'll stay taut for a while. That's literally because you don't have the energy in your muscles anymore to get them to relax. So they're just going to stay in that position until the proteins eventually degrade, and then the muscle will relax. Now, we talked a little bit about the muscle fiber types. Here is a good way, I specifically will get to the graph in a moment, of looking at the differences between our type 1 or the slow twitch, type 2A fast twitch, and type 2X fast twitch. Now, remember, they're going to go from slowest to fastest, and also the least fatigable to the most fatigable. So if you look in the bottom right, you can really see that major difference in power. So if you're trying to work, if you're trying to use eugenics to essentially have the perfect athlete for a power sport, you want somebody that's going to have a crazy amount of 2X fibers. If you want to go ahead and try to breed a great long distance runner, you want the opposite. You want to have a lot of type 1 muscle fiber. Now, still a little bit of everything, but we definitely want to make sure that we're leading more towards the other. Now, keep in mind the difference in the motor unit size, guys, as far as getting them to be recruited, and that we're going to be recruiting a lot more individual fibers per type 2 motor neuron compared to type 1. And one thing that we haven't touched on yet, which is going to be the relationships we're going to have with what's known as a hybrid fiber. So if we are to actually take and look at muscle under a microscope, your muscles, aside from your heart, are not pure type 1 or pure type 2 or type 2A or type 2X. You're always going to have a certain amount of hybrid muscle fibers. And hybrid muscle fibers are really neat because that literally means we have the ability to adapt to the demands that we need to place on the body. So a certain number of muscle fibers you have in your body, and literally, let's take your quads, for example. You're going to have a certain amount of muscle fibers in your quads that are pure type 1, a certain amount that are pure type A, and those of you guys that are genetically lucky, a very small amount, or a small amount that's pure type 2X. What we're going to have a lot of is what's known as hybrid fibers, meaning we're going to have some fibers that literally the inside of the cell is made up of both type 1 and type 2A, or 2A and 2X, or even the most interesting hybrid fiber, literally some that are going to be made up of type 1, type 2A, and type 2X, where depending on how you train, those fiber types are going to transition more towards how you're actually training. And so if you train aerobically for a really long period of time, so type 1 muscle fiber, you're going to see those 2A/type 1 fibers transition more to type 1. You're going to see those 2A and 2X fibers transition more to 2A. And then if you want to become a really good power lifter, Olympic lifter, strength power athlete, you're going to see your fibers actually transitioning to the 2A fiber type. Your 2X fibers are effectively referred to in the literature, colloquially referred to as couch potato fibers, in that most people that are really highly trained, and we're talking like Olympic level weightlifters. I've seen the data. My old advisor is the one that did the research. Out of, I think it was about 10 different international level Olympic lifters from the US, only one of them had any appreciable amount of 2X. Everything else was 2A, because as we train, we're going to be transitioning more into fibers that can do a greater amount of work. So true, pure 2X fibers are pretty rare. And people like Usain Bolt and some of your ultra high level sprinters and otherwise, there are some people that are naturally gifted with it, but it's pretty rare. Any questions on hybrid fibers? Thank you for voting no, whoever's doing that. I appreciate it. All right. Well, I guess I'm just knocking it out of the park, so let's just keep it going. Now, another big property of working with muscle is understanding what's known as the length tension curve. Okay. Now, what we're looking at here is active force production, not passive. Okay. Passive muscle, meaning as we stretch a muscle out further and further, it's actually going to be producing more force. All of you guys know this. If you've ever tried to stretch someone's hamstrings, or you've ever had someone stretch your hamstring where it just feels like you're pulling back a bowstring as we go because of that tension on the line. Now, notice it says sarcomere length. So when we have a sarcomere at its resting length, so it's going to be essentially like what would be the midpoint on the range of motion, that's typically where we have the greatest amount of crossover between our myosin heads and then actin grabbing hold. As we lengthen the fiber, so we're going into a wider position, it's going to be more like number 1, where you see it's that wider position, so we don't have as many myosin heads that can grab and ratchet onto actin. And then when we're in the shortened position, we're going to not be able to produce as much force because literally we're essentially butting the actin strands up against each other, and you can't go any further than that. So this gives us a couple things we need to think about when we're working with athletes, okay? If we know we're going to be actively the strongest in the midpoint of the range of motion, and we're going to be the weakest at the shortest position and the most lengthened position, what does that mean about flexibility and mobility for an athlete? What's the advantage there? If we take somebody that's really inflexible compared to somebody that's really flexible, what's going to be the key difference when you're looking at their potential length tension curve? And you guys can unmute yourself or write something in the chat. Okay, we're super quiet, so somebody give me something. Okay, so from John Nelson, would there just be lower levels of developed tension? Good question. Now, first and foremost, we're talking about just relative to the individual. So each person, you're right, is going to have different abilities with strength. If we somehow had two people that had the same amount of maximal strength, the problem is the tighter athlete is only going to be able to display that amount of strength for a shorter effective range of motion. Now, if you're doing something, oh, good. The more flexible someone is, they might have less ability to create maximum amount of force. Not really. Instead, what we're doing is by making them more flexible, we're widening that length tension curve. So the peak force is still going to be the peak. The key is now they're going to have a greater dispersal, so they're not going to essentially hit that peak so quickly. They're going to have a wider range, meaning if someone's really inflexible, like they can barely get themselves into the starting blocks for a sprint, they're not going to be very powerful. But if they're more than flexible enough that they can get into a good position, that they're in that more optimal range of the length tension for a curve, they're actually going to be able to produce a greater amount of force. So thank you guys for giving me some points back. Does that make sense? As far as it's an advantage to actually have an optimal or at least a better amount of flexibility as opposed to being really tight when we're looking at sports, especially things where you got to be able to move through a large range of motion. Awesome. And so the last thing we're going to touch on is what's known as the force velocity curve. Now, this can seem a little unintuitive when we're looking at isometric to eccentric action, but the concentric should hopefully be straightforward for you guys in that as you are moving faster and faster, you are not able to apply as much force. So what this means is that the faster we're moving, the harder it is to push any harder. This is the reason why you can always deadlift more weight than you can clean, and you can always clean more weight than you can snatch. And you can snatch more weight than you can throw 10 feet over your head. Because as the weight gets heavier and heavier, you're not able to move it as quickly. Now, why this matters is because in sport, if we want to be able to move the same weight object even faster, we need to get stronger. Because notice, guys, it's going to be relative to the maximal force ability. So, for example, Tyler's on the cheerleading squad. It turns out if the guy isn't, well, Tyler, can you unmute yourself?
What's up?
What did I used to give John trouble about all the time?
That he was little.
And not necessarily little, that's a
He didn't get in the weight
thing,
room.
but what specifically about it?
Just he didn't get in the weight room.
Because he wasn't strong enough.
Right.
And could John put up and throw elite stunts with every girl on the team?
No.
What was the answer there, Tyler?
No,
Why is that?
because he wasn't strong enough.
Exactly, okay? There's a reason why the stronger you get, the easier it is to do activities of daily living, but it's easier to be more powerful. Now, your power output, thank you, Tyler, is going to come down to things like muscle fiber type, aka your genetics. 50% of your muscle fiber type is simply determined by who your parents are. The other 50% is how you train it. So we've got a certain amount of flexibility, but at the same time, a solid amount of the blueprint was thank you or curse you, mom and dad. So when you're working with athletes, we want to literally make someone stronger, or at least strong enough that they can go at a higher speed. Because the reason you're not able to sprint faster isn't because your legs can't move fast enough. It's usually simply because you can't apply force fast enough into the ground to make yourself move any faster, and or produce the force to get your leg back in front of you in the period of time you need to in order to go any quicker. So our peak performances are going to all relate back to this force velocity curve. The other thing to keep in mind when you're looking at this force velocity curve, guys, is notice the fact that you technically are going to be stronger when you're doing an eccentric, which if this was a normal semester, I'd say go to the rec center and watch the bros bench press. And specifically, anytime a guy says like, yeah, I'm gonna do a set of 5, you got me? And then they'll do 1, and then it'll just be stuck there. And what they meant to say is, I'm gonna have you do 5 upright rows that get heavier while I don't really do 1 rep. So yeah, you can always, or the best is when somebody tries to squat more than they can, where it's like, they can definitely lower the bar. You can always go to the bottom in the squat. You might just not make it back up. So that's it for chapter 1 of the major things that you really need to make sure you're understanding, from satellite cells to obviously the basics of muscle physiology, how it's going to contract and how it's going to relax, along with properties inside of it. I apologize, guys, but I'm interested. Was that on squat or was that on bench press?
Parker tried to go from 275 to 305 on bench press, and I already was done with my workout, so he asked me to come spot him. I asked him what I was doing. He said 305, and I said, "Did you just do 375?" And he said, "Yeah." So it was like, "I'm gonna try to get it 3 times." I said, "Okay." I said, "Do you want me to lift it off?" He said, "No," and I said, "Okay." So he lifted it off. It just like crashed down on his chest, and I just kind of like laughed a little bit, but then like helped him up.
Yeah, just a little pro tip, guys. Anybody who is asking you to essentially save their life 5 times in a row or some nonsense like that, I'll give them the lift off, and then if they say they're doing 5, I'll just stare at them. So I'll just have the bar on their chest, and until they say help, I'll just stare at them. And then when you pick it up, try to pull it in the rack. But if they're like, no, I'm going for another, you let them go down, and you just stare at them again. Like, I don't understand. This is a really long pause. This must really suck. Because you got to teach people lessons sometimes. But anyways, that's me being a jerk, and you guys shouldn't be like that. Any other questions as of right now over the basics of chapter 1? I know there's got to be something out there. You guys can put it in the chat, or you guys can go ahead and once again, unmute yourself. Anything you guys want to go through again. Otherwise, you guys are going to have the quiz. Remember, lab on Friday is going to be outside. We're going to be doing that behind that little patio area behind the old rec center. If weather just goes to heck in a handbasket, then we are going to figure something else out. What that is, I do not know yet. Figure worst case scenario, we'll actually be in the lab. Okay, to get to the lab Friday, do we have to go through the old rec to get out the back? Yeah, you can just walk around it, Haley. Just walk around it. The key is you got to go through because I think they still have it padlocked on one side, like where the football visiting bleachers are. You just need to go around the other side. Do we need to print the lab and bring it with us? No, I would suggest if you guys have a laptop or otherwise, just bringing that and just already having the Word document there. And you can always just bring a notebook and just fill out the information that you're going to need on the lab and then just type that in later to submit it online. Honestly, guys, it makes it easier for me to grade it, and then make sure that you guys always have your grades online so you can see it. But if you guys want to print it off, that's always an option. I just like trees and not using ink if I can help it. So yeah, that's an option. Yeah, no worries. So the thick filaments is myosin. Now the other component inside there is what's known as titin. Titin is actually going to work as effectively a bungee cord that's going to make sure that myosin is going to stay aligned in the center of actin. So if we're looking at this picture here, guys, titin would be a thin bungee cord going from the Z line, and that's where the actin strands are going to come together, go over to the myosin. Now, these Z lines are actually what you're going to break when you're doing hard resistance training. So we talk about like delayed onset muscle soreness, which we'll get to later on this class. That's literally where it's happening. You're snapping those. And yeah, there's a reason why it hurts. The other side of it is thin filaments, or what's known as actin. Now, on actin, remember guys, is both troponin and tropomyosin. And at the very end of actin is another protein known as nebulin. Nebulin is a ruler that effectively is like, that's as long as it's going to be. And Zach, if you need me to follow up, I will. Madison asks, why are the fastest cross-country runners always small if you need to be strong to be fast? Power to weight ratio. No, so that is an absolutely great question, Madison, because it's like anything else. When we think about performance with athletes, I often like to think about cars. So most Americans are like an old rusted out Pinto that if you stomp on the gas pedal, they're probably going to die. Sorry. But when you're talking about cross-country athletes, you're really you're talking about like a Prius. You're talking about the most light, efficient car you can have that's going to get you to cover a pretty big distance. So you want in that sport to have the smallest, lightest car you can, and then to have a big enough motor to keep that going at a pretty good clip for whatever time you can manage. There's a reason why if I told the best player on the cross-country team to take a full sprint at the worst offensive lineman on our football team, that cross-country runner could quite possibly die from that collision. And the offensive lineman would be like, what was the point of that? Because the offensive lineman is more like let's be honest, they're more like a freaking tractor trailer. They've got a lot of power, but they also got a lot of weight. And so when you're working with your athletes, you need to think about what is the adequate amount of strength they need for them to be good at their sport. And then what we're going to get into in chapter 2 is we're going to talk about the energy systems, and how each of those are going to contribute to your ability to perform at your given endeavor. So you're right. It's not as simple as just be stronger, because then power lifters would be good cross-country runners, which is not true. Instead, it's that power relative to body weight. So the only question that I'll throw, not necessarily throw back, but if you look at a lot of those cross-country kids that we have here, they by no means are really that strong, but they also have a very light body. So like we were testing those kids earlier, I cannot beat a single one of them in a mile, a 5K, a 10K, or anything along those lines. If we just want to do it like we're both in, a cross-country uniform, right? Dear God, they definitely don't have one my size on this campus. However, I can beat them at the mile. It's going to be very simple. We're going to do a mile run at a system mass of 300 pounds. So what that means is I'm going to put on a 90-pound weight vest, and I'm going to go do a mile. Those cross-country kids, some of them are going to literally have to strap 200 pounds to their body, and I would love to watch them try and walk like that. So yes, they're not as strong as I am, but they also have so much less weight they have to carry. It makes everything a lot easier. So it's, I guess, and I might be just kind of beating the dead horse at this point, but you never see cross-country runners that look like me that win, and you never see power lifters that look like a cross-country runner that win. Does that answer your question? That's a really good question. Cool. Any other questions you guys want me to go ahead and talk about on the chapter? Man, it's so weird when I'm only talking to myself. I feel like I go really fast because we're already done with chapter 1 and we still have almost half an hour of class left, which means we're going to keep lecturing on to chapter 2. Give me a second. I'm going to stop sharing screen because I don't want you guys to see all the pictures of cats on the internet that I've been staring at on my laptop before we got on this wonderful Zoom call. But please, if you guys have any other questions over chapter 1 or anything else involving, you know, just class material, expectations and everything, just throw them up in the chat or please unmute yourself. Because I do not like talking to myself. All right, guys, so now let's start talking about the wonders of energy systems. So the first thing we're going to talk about is basic substrates, okay? These are going to be the things that we're going to break down in order to make ATP, excuse me. It's going to be carbohydrates and fat. Those are the major two. You will use protein as a fuel on occasion. It's pretty rare. It's really going to be coming down mostly to carbs and protein, or carbs and fat. Bioenergetics is the sum of all of these processes of us breaking down all these different substrates to make energy, okay? Metabolism is going to be all the anabolic, so building up, and catabolic, breaking down reactions that we're going to have in the body. Every single day, guys, you've got to keep your heart beating, your diaphragm's got to keep contracting, your brain hopefully is working. We have all these systems that no matter what you're doing, they have to keep moving. And then if we add exercise on top of it, we're obviously going to have even greater caloric demands than we would have otherwise. Now, the way that we're actually going to measure how much energy you're using is going to be in what's known as calories. Now, the little c calorie is the amount of energy it takes to increase 1 gram, aka 1 milliliter of water, 1 degree Celsius. We look at calories as the big C calories, and that is 1,000, so it's a kcal. So when you like look at the nutrition labeling, it's already naturally in kilocalories. So this is why when you start exercising, you warm up because you're releasing anywhere up to 70, it could be even high as like 80% of the energy that you produce from exercise is really just wasted as heat, because the body is not 100% efficient. No machine is. So we are going to get this energy by snapping individual bonds. Hopefully a lot of the stuff is going to seem as review. Now at rest, depending on your previous meal, you're going to be using more fat or more carbohydrate. You figure normally it's going to be about a 50-50 mix. As we're going up in exercise intensity, we're going to be relying more on carbohydrates. As we're going to be increasing our duration, we're going to be utilizing fats more as a fuel. So as far as the total amount of calories you have stored on your body, and this is based on an estimate for a 143 pound guy with 12% body fat, so relatively lean, smaller dude. The total amount of calories that's going to be stored in the form of glucose is going to be a little under 2,500 calories. Now, it takes a 154-pound European male about 100 calories to cover 1 mile on the ground. Woo. Now, here's the thing. That means with relatively topped off glycogen, you've almost got enough carbohydrate in this example to cover 25 miles on straight carbs. Now, muscle glycogen is specific to the muscle it's in, so it's kind of hard to free it up. You can do it through the Cori cycle and otherwise, but it's just not as efficient. Liver glycogen can go anywhere it needs to. And this is also denoting that you're only using pure carbohydrates as a fuel. Now let's look at fat. Fat is going to be that 9 kcals per gram, so it's a lot denser compared to carbs, which is only 4. And even in this relatively lean guy, you're talking about a total amount of fat stores of almost 75,000 calories, meaning this relatively lean dude could walk all the way from Richmond, where I'm at currently, to the Atlantic Ocean and still have some calories left over on fat stored in his body. That's how much energy we have stored in fat. 1 pound of fat, guys, is about 3,500 calories. The reason I say about is because fat cells also have water in them and not just fat. So when you actually start to lose weight, you're depleting the fat inside of the adipose cells, but there's water that'll pull in with it. So that's why you can kind of look the same size for a little while, then all of a sudden have your weight just kind of drop somewhat drastically. And that's literally due to the cessation. And then we have issues with the fact that fat cells never want to go away, the bastards. But that's a different story for another time. Does that make sense as far as how much of each we have stored for long term and what we're going to be using acutely? Now, if you understand this graph here, you're going to have a pretty good understanding of how we're going to convert from one fuel to another, okay? So hence we start off at the top with our food intake. Obviously, each macronutrient is broken down in its own way. So we've got our proteins, carbs, and fats. And then they're going to be broken down into their smallest components. So for fats, this is going to be fatty acids plus glycerol. That's what makes up a triglyceride, 3 fatty acids and 1 glycerol. All carbohydrates are effectively going to be modified into glucose. So we maybe took and had fructose, had galactose, they're going to be converted into glucose. And then proteins are going to be broken down into their individual amino acids. Now, these proteins are stored as body protein, which effectively we're talking about muscle. So you have that for your long-term storage source of protein, which is not a great choice to try to use because that's the equivalent of saying, we're going to fix the car by literally breaking off parts of the car and melting it down. So hence, during starvation, you will start to lose muscle mass. That's normal. Now, carbohydrates can be stored as muscle glycogen, can be stored as liver glycogen, or going to get used as fuel. And then any excess, once we top off the glycogen, or if we do like a really massive bolus of carbohydrate, it's then going to be converted into fat and stored appropriately. And so once it's converted to fat, obviously we can still go back into fatty acids and use that for energy. Now, all of those are going to be contributing to our overall metabolism. So if you understand how each of these are flowing forward, you've got a pretty good idea of the basics here. Now, what's fascinating is the research really shows that you can go really high on protein intake, and it tends to not negatively affect your body composition or cause you to really gain any appreciable amount of body fat, but it doesn't really seem to help you gain extra muscle. However, on the other side, excess carbohydrate is always going to be converted into fat, and excess fat is already fat, so let's just store it away and make us feel self-conscious on the beach. Now, our body is all about efficiency. It doesn't want to burn a single extra calorie than completely necessary. So we're going to use this number of systems of what's known as negative feedback to keep us from ever breaking down more than we need to. So if how much we have available is always going to affect our metabolic rate. If we have more substrates available, we're going to utilize that pathway more, meaning if you had more carbs recently, you're going to use more carbs for fuel, or for energy, for whatever you're doing that day. If you've had more fat for your intake that day, you're going to use more fat as a fuel. That's just what the body's going to do to make sure you're taking care of your needs. Now, enzymes are going to be the way that we're going to decrease the activation energy and allow ourselves to go through and do all of these pathways far more efficiently than if we were just kind of hoping it was going to happen. Now, the rate-limiting enzyme is usually an enzyme that happens at the beginning of the cascade, and this is going to create a bottleneck. So this is meant to be the one that controls the speed, and it's usually going to be influenced by the products at the end, hence the negative feedback. So once we have a greater amount of the products at the end, it's going to shut down that enzyme so we're not producing any more than we need to. A great example of this, guys, is like the thermostat in your apartment or your house. So that, obviously it's a pretty nice day out today. So let's say you've got your thermostat set for 78 degrees. Well, it's not that hot today, so your AC might not ever turn on because it never gets warm enough that it has to turn on. But the second it's going to get the house up to 79 degrees, your AC unit's going to turn on, your blower is going to turn on, it's going to bring your temperature back down to 78. Once it gets under 78, it's going to shut it off again. And then that's going to be negative feedback. So once we get to where we want to be, we shut down the system. It's good because it's efficient. It's bad because we can eat nearly an infinite amount of calories, and the body is like, I don't realize that I'm eating because of insert number of reasons, but I don't want the negative effects on my health. It simply is like, oh, extra calories. Let's store this for later. We might need it. Now, the universal energy currency of the cell is what's known as adenosine triphosphate, also known as ATP. This is what we're using for our major energy currency for muscle contraction, for building proteins, for a myriad of other metabolic processes throughout the cells. So it's really simple. We take ATP plus 1 HTO, you break it down into ADP plus 1 phosphate, and we have energy. Now ADP doesn't have as much energy, so we're going to try to replenish that, and that's going to be breaking down once again those macronutrients. Now this can occur with or without oxygen available. If we're replenishing ATP without oxygen available, that's anaerobic. With, it's aerobic. Now, our first energy system is our ATP PCR system. Since ATP is very limited, but literally you use about 20 to 40 kilograms of the stuff every single day because we're constantly recycling. That's why we don't have to have 20 kilograms of ATP built into our body. We then have our glycolytic system, which is going to be anaerobic, lasting typically up to about 2 minutes. Then we're going to have our oxidative system, which has two major branches, which is going to be our aerobic glycolytic, which is going to last sometimes as little as maybe an hour. If you're really doing good on glycogen strategies and otherwise, you might be able to get it to last for about 3 to 4 hours or a little bit further. And then we have our beta oxidation, which is going to be our fat metabolism, which is slower still, but has a much greater capacity, like we talked about, of being able to literally be able to walk to an ocean. So the ATP phosphocreatine, so PCR system, is literally going to be anaerobic. It has one enzyme, which is creatine kinase, and all it's doing is taking the phosphate from phosphocreatine and giving its ADP to replenish ATP. It's only going to last about 5 to 6 seconds. So if you guys want a good idea for when you're really going pretty heavily on your ATP PCR, is go out to a track or go outside and just run, after you warm up, run as fast as you can. Like just try to sprint as hard as you possibly can and think about how few seconds that does not feel miserable for. Because as soon as you're like, oh, my lungs are burning and my legs are burning, that's when you're going heavily into anaerobic glycolysis. Now, this energy system is really important because, well, 5 or so seconds in, the normal world, that's about how long a football play lasts. That's how long a play in a sport like baseball and softball can last. So that's going to be the energy system that they're really using to play the sport, but then we still need to regenerate that phosphocreatine again and regenerate that ATP, and that's where our aerobic systems are going to become more important. So phosphocreatine, if we've got a lot of ATP in the cell, it shuts it down. If we have low levels of ATP, we're going to be using it. Really simple. We then have our anaerobic glycolytic system. Okay, this is going to be the one that's going to give us 2 to maybe 3 ATP if we started from glycogen for every 1 mole that we put in. It's only going to last us about 15 seconds to 2 minutes, and it is miserable, absolutely miserable. How many of you guys, and you can put it up in the chat or otherwise, did anyone here run the 400 meter or 800 meter in high school? Okay, so those of you guys that did it, how many of you guys either threw up or nearly threw up from running that 400 meter? Yeah. The anaerobic glycolytic system is useful, but it hurts like a son of a gun. And you can drop your pH so low because you're producing lactate. Lactate isn't the problem, it's that proton that comes with it, aka hydrogen. As your pH level goes down, because we got an accumulation of hydrogen, that is going into our bloodstream, so it's dropping our blood pH. When your pH gets low enough, the chiasmatic nucleus inside of your brain is going to literally say, I think we're poisoned, and will then force you to vomit. So indeed, Cody, 400 meters are blah. And so it's completely normal. And same thing if any of you guys have ever done really high rep squatting, really high rep deadlifting, anything where you're just doing a massive anaerobic load and you're like, I'm really nauseous right now. That's literally because you dropped your pH because of using anaerobic glycolysis. So we're going to start from glucose or from glycogen, which will be converted into glucose 6-phosphate. Just means there's literally a phosphate on the 6th carbon of glucose, because glucose is a 6-carbon sugar. and we're going to use 1 ATP to activate, okay? From there, we're going to go through all the enzymatic processes of glycolysis, and from there, we're going to net effectively 2 ATP if we started from glucose because it required 2 activation. We got 4, so that means we net 2. Or 1 activation if we started from glycogen. So we paid 1, we got 4, so we net 3. This doesn't give us a lot of ATP, is a really inefficient way to use carbohydrate, and it's going to be giving us that wonderful lactic acid, which immediately converts into lactate. Lactate is not the problem, guys. Lactate is a fuel source. You can actually take lactate as a supplement, and it can have positive effects on performance. Now, if you try to take a syringe full of hydrochloric acid, that's going to burn through you and be very, very bad. Now, once we get our pH down low enough, muscles literally won't contract like they're supposed to. And once again, those of you that ran 400 meters, those of you guys that have done real hard anaerobic work, you know exactly what I'm talking about. But this at least gives us an avenue outside of the ATP PCR system that we can use when we happen to not have enough oxygen available. And so this allows us to keep up exercise output when otherwise we wouldn't be able to keep doing what we're doing. So the major rate limiting enzyme is what's known as phosphofructokinase, PFK. Okay, where this again is going to detect the level of ATP, and if it's low, it's going to turn it on. If it's high, it's going to shut it down. Now, other products of the Krebs cycle, so this is going to be like acetyl-CoA and high levels of NAD are going to also turn this on. And once we go into aerobic glycolysis, now we're talking about using the citric acid cycle and the electron transport chain, which are also both specific to being inside of the mitochondria. And this is the one that's going to last for a far greater duration, okay? Because we're aerobic. And now instead of only netting 2 or 3 ATP, we're going to net 32 to 33, depending on where we're starting. And if we're using beta oxidation, for breaking down what would be a fat like palmitoleic acid, is going to give us about well over 100 ATP because we've got so many so many single carbon bonds that we can use to give ourselves energy. And this is going to be able to last for possibly a couple hours if we're talking about doing this aerobically with glycolysis, or literally could last us, depending on the amount of body fat somebody has, could quite possibly last them maybe even a year. No nonsense. Like never have to take in an actual calorie, just do vitamins and minerals because they've got such great reserves of fat on their body. So we're going to go ahead and stop here, and we'll take over going a little bit deeper into the citric acid cycle whenever we are going to meet up on the interwebs on Monday. What questions do you guys have for me? And I'm actually going to be able to get you guys done. So I guess that's one of the problems or one of the pros of doing this online, which is I kind of cover material faster, which is, well, I guess I'm considering that a pro, but a lot of you guys are probably like, I'm going to have to watch this again a couple times because he doesn't stop talking. I don't even think he breathes. That's okay. That's okay, Tyler. So now one thing that Zach Maston was asking, which is whenever we meet for labs, if we could effectively kind of do like a small study group, and that's perfectly fine. You know, we're going to meet out there. The first lab, remember, is just going to be doing the hand grip dynamometer. I'm going to bring gloves out there, so we're going to have medium, larges, and XLs. So if you've got like massive banana hands, you might be in trouble. And if you've got like little baby hands, then I don't know, they might be a little too baggy. But aside from going through and having you guys do the lab, then I'm more than happy to go ahead and talk with you guys and we just have the kind of the conversation outside as to, you know, anything that we've covered so far over chapter 1 and what we're getting into chapter 2. Make sure you guys take that quiz over chapter 1. Remember, you only get to take it once, so focus up and do your best. Make sure you're doing the homework, so you're also working on the homework for chapter 2, and then ready for lab on Friday. Questions, comments, concerns? All right, guys. Well, I'm going to go ahead and we'll call it a day there. You guys have yourself